This Chapter 2 maps out the calculation of VaR under normal distribution assumptions for basic FX, interest rate, commodity, and equity derivatives. Our first illustration of the calculation of VaR for a derivative instrument returns us to the US bank, which this time is using a 4% 12 by 24 forward rate agreement, or FRA, to hedge a future interest payment on a $10 million loan indexed to 12-month LIBOR. We would say in this case that the US bank has bought the FRA. With regard to this 12 by 24 period, the LIBOR fixing under the loan will occur in 1 year, while the interest payment, of course, will be payable in 2 years' time. For the FRA, the convention of the British Bankers Association, widely used in most markets, is to effect the actual settlement of the FRA as soon as the LIBOR fixing has occurred, i.e. at the beginning of the 12 by 24 period in this present case, and to adjust for this early settlement by discounting the payment otherwise due at the end of that period at that same LIBOR fixing rate. We will ignore this convention in our discussion since it does not affect the price sensitivity of the FRA, since early settlement does not affect the PV of the anticipated cash flow. We recommend you review our module Interest Rate Forwards and Swaps if you need a detailed refresher on the characteristics of interest rate forwards. The fair value of the FRA contract, calculated by means of the equation about to appear, equation 1, depends on the evolution of the 12 by 24 FRA market rate, F in the equation, which simply states that the fair value of the contract equals the present value of the difference between the 4% rate locked in under the contract and the 12 by 24 FRA market rate as it evolves, where ZC2 is the 2-year zero coupon rate. We should emphasize that this equation is accurate only as of this exact instance in time, and that as time passes, the tenor of the forward for determining F and the applicable discount rate should in principle be adjusted to reflect the diminished horizon. The contract's fair value is seen to be positive if F exceeds 4% and negative if F falls below 4%. Now, the instantaneous forward rate F depends exclusively on the spot 1-year and the spot 2-year zero coupon rates, ZC1 and ZC2, as per the following equation number 2. Replacing F in equation 1 with the expression above in equation 2 leads us to fair value equals what you see here. And finally, rearranging the terms reveals that the fair value equals this quantity here. It follows that an increase in ZC1 has a negative impact on the contract's fair value, while an increase in ZC2 has the opposite effect. Equation 3, the most recent equation we wrote, also indicates that the FRA contract is equivalent economically to a position in 2 zero-coupon bonds, and specifically a long position in a 1-year zero-coupon bond paying the notional amount at maturity, and a short position in a 2-year zero-coupon bond paying at maturity the notional amount plus a coupon based on the original 4% FRA contract rate. Furthermore, this observation can be extended to any m by n FRA for any values of m and n, and allows us to deconstruct the position into a long-short combination of two zeros, one zero paying the notional amount on date m, and the second zero maturing on date n, and paying, as before, the notional amount plus a coupon based on the original contract rate under the m by n FRA. If the bank is paying the fixed rate under the FRA and receiving the spot LIBOR, the bank is long the shorter bond and short the longer one. If the bank is receiving the fixed rate, the bank is long the longer bond and short the shorter one. Turning now to worksheet RS-FRA, cells C23 and C24 provide first as inputs the current levels of the relevant risk factors, i.e. the 1-year and 2-year zero-coupon rates of 3% and 3.5%. The fair value of the position in cell C13 is 0, since the bank has only just executed the FRA, presumably at market rates. We now simulate a positive 1 basis point shift in zero coupon rate for 1 year, but a negative 1 basis point shift in the zero coupon rate for 2 years, to bring about in each case an adverse impact on the fair value of the position, as explained previously. If the bank were receiving the fixed rate under the FRA, we would use shifts with the opposite signs. We have programmed in cells C16 and D16 the formula for the forward rate using adjusted zero coupon rates that reflect the 1 basis point shifts. Then in cells C17 to D17, we revalue the position as the present value of the notional amount multiplied by the difference between the new forward rates and the old one. Given the initial value of 0 for the position sensitivity to shifts in the risk factors appearing in cells C18 and D18 is quite simply equal to the position value after the rate shifts. To confirm the equivalence of the FRA position and the long-short combination of zeros mentioned before, we have also calculated the fair value of such a combination, namely long a $10 million by face value 1-year zero coupon bond, and short a $10.4 million 2-year zero coupon bond by face value. Cell G25 in this table here, which is labeled, as you'll see in a moment, base case scenario, reveals the position's fair value at inception to be 0. The table starting on row 28 calculates the impact of a 1 basis point increase in the zero coupon rate for 1 year, with the negative $423 expected in fair value indicated in the cell G32. The same steps, but with a 1 basis point decrease in the 2-year rate, are repeated in the table starting here on row 35, confirming once again a revised fair value of negative 1,876 in this cell G39, equaling exactly in both cases the numbers previously calculated over here in cells C and D17. Continuing our analysis of price sensitivity for derivative instruments, we assume now on this worksheet RS-FX forward that the US bank has just entered a long 10 million euros 6-month FX forward contract, i.e., it has bought 10 million euros 1 year forward against US dollars. The worksheet begins with the relevant market data in cells C5 to C7, namely a euro-dollar spot of 1.4 and 6-month dollar and euro interest rates of 2% and 4% respectively. We have next programmed in cell C8 the familiar formula for an FX forward that is derived from the FX spot rate and the term and base currency interest rates, revealing a euro-dollar 6-month forward rate of 1.3865. We have decompounded the interest rates here by means of a square root operator, which is a little unconventional. You can change that if you prefer to the more conventional method of simply dividing by 2 or of using a specific day count adjustment. Examination of this formula leads to the recognition of 3 risk factors for this instrument: the euro-dollar spot rate and the 6-month dollar and euro interest rates appearing here. In parallel with the preceding discussion, we emphasize that the passage of time would cause us to replace these 6-month rates with rates for a diminishing tenor, a subtlety we will again ignore for the rest of this discussion. The fair value of the position is once again 0, here at inception, since the bank has just executed the forward contract, presumably at the market rate. As before, we calculate next the risk factor sensitivities using this time a 1% shift in the FX spot rate and an absolute 1 basis point shift for the 2 interest rates. Again, we tread cautiously regarding the direction of these various shifts to bring about an adverse impact on the position value in each case. So this time we use a 1% decline in euro-dollar spot, a 1%, 1 basis point decline in the 6-month dollar interest rate, but a 1 basis point increase in the 6-month euro interest rate. And again, if the bank were short the 10 million euros forward instead of long, we would use the same magnitude of shifts, but with opposite signs in each case. Over here in cells C17 to E17, we calculate the forward rate after giving effect to the assumed shifts in risk factors, and then calculate in cells C18 to E18 the value of our position, specifically equal to the notional amount in euros multiplied by the difference between the new and old FX forward levels and discounted appropriately to today's date. Given its initial fair value of 0, the position sensitivity to shifts in the risk factors appearing here in cells C19 to E19 is quite simply equal to the position value after these shifts. Thus far, we have based all our examples on situations in which the fair value impact on the underlying position bears an almost linear relationship to the changes in the risk factors. In such instances, the impact of a movement in any risk factor in excess of a single unit shift can be reasonably approximated through simple multiplication of the movement by the position sensitivity per unit shift. We now address situations in which this relationship is not linear, but rather is curved, i.e. carries a certain degree of convexity. For our first example, we leave behind derivative instruments for just a moment and consider a fixed rate bond. Assume the US bank has just bought a newly issued US dollar bond with the following characteristics. We value this bond off the zero coupon yield curve, and specifically the 1-year, 2-year, 3-year, 4-year, and 5-year zero coupon rates, with each of these maturities corresponding to the date of one cash flow under the bond. In the case of an option-free bond, the relationship between price and yield movements is known to be convex to a greater or lesser degree, as illustrated in the following graph depicting the price-yield relationship for two bonds labeled Bond 1 and Bond 2 with visibly different degrees of convexity. The greater curvature of the solid green line compared to the solid red line reflects the greater convexity of Bond 2 versus Bond 1. For any given yield movement, we can approximate the percentage change in a bond's price by means of the following equation number 4, discussed extensively in our module Bond Fundamentals. Equation 4 is illustrated graphically for a typical bond in the diagram appearing now, in which the dashed blue line is based on modified duration alone. The dashed red line on both modified duration and convexity, and the solid red line on the precise price-yield equation. The impact of convexity is best understood as the deviation of the dashed red line from the dashed blue line, and its far greater proximity to the solid red line. To repeat, neither the dashed blue line nor the dashed red line depicts the exact price-yield relationship. Only the solid red line does that. But the inclusion of the convexity effect in the dashed red line has reduced quite dramatically the extent of the inaccuracy appearing in the dashed blue line. The inputs for equation 4 can be calculated analytically through the exact mathematical formulas for modified duration and convexity applicable to all bonds whose cash flows are fully determined in all circumstances, namely fixed rate, option-free bonds. For other bonds, numerical approximations for these two inputs are required, of which several are available. We will illustrate both types of calculations next. The first part of equation 4, which relies on modified duration only to produce a linear approximation of the percentage price change, is very similar in effect to our previous examples, in the sense that it produces a strictly linear relationship between shifts in the risk factor and the position value. We will frequently refer to this effect for the rest of this module as the linear approximation effect, or sometimes the first order effect. The first part of equation 4 requires an input for modified duration, for which practitioners often resort to a numerical approximation provided in the formula appearing now, the derivation of which is outside the scope of this module. Here, P is the bond price at the current yield level Y, P plus is the bond price at yield level Y plus 1 basis point, and P minus is the bond price at yield level Y minus 1 basis point. The second part of equation 4 requires an input for convexity, for which practitioners often resort to another numerical approximation provided in the formula appearing now, the derivation of which is also outside the scope of this module. Geeks will wish to know that equations 5 and 6 are rooted in the mathematics underlying the first derivative and the second derivative of an algebraic function. You can learn about this topic in any number of established texts, as well as in Wikipedia on these links here. Returning to our example with the 5-year bond, cells D22 to D26 of this worksheet RS bond numerical list the spot zero coupon rates for the 5 relevant tenors. This first table, labeled base case scenario in red, calculates in cell F27 over here the position's fair value to be 10,042,996. We now derive the linear sensitivities of the bond to our 5 risk factors, assuming an adverse shift of 1 basis point in each of these risk factors. Again, an increase of 1 basis point causes a negative impact in the position's value. Cells C13 to G13 indicate the new levels of the 5 risk factors after the assumed shift. To estimate the impact of convexity via the approximation from equation 6, we initially calculate the impact of unit shifts with the opposite sign, minus 1 basis point in this case. In the tables appearing below the base case scenario table, beginning here on row 30, we revalue the bond following each unit shift and opposite unit shift in each of the individual risk factors. Here's the 2-year 0, the 3-year 0, the 4-year 0, and so on. For example, these cells here, B30 all the way to F37, we cannot quite squeeze them in the screen, revalue the bond after a positive 1 basis point shift in the zero coupon rate for 1 year, with the new bond value appearing at the bottom right here in cell F37. And similarly, the cells beginning B40 and going all the way to F47 perform the identical calculations for an opposite, i.e. for a negative 1 basis point shift in the 1-year zero coupon rate, revealing the new bond value over here in cell F47. We repeat the same steps as we mentioned a second ago for the other risk factors, i.e. for the 2-year zero coupon, the 3-year zero coupon, and so on, in the tables appearing successively further down. You should not be surprised to discover that the impact of a 1 basis point shift in ZC5, right at the bottom here, is substantially greater than that of the other 4 risk factors, since ZC5 has an impact on the bond's final coupon, but also its far greater principal. The bond values resulting from the positive shifts in risk factors are finally summarized in cells C14 to G14, and the ones resulting from negative shifts in the cells underneath. The position linear sensitivity to each risk factor unit shift is calculated simply as 1/2 the difference between the position value after a positive unit shift minus the position value after a negative unit shift. More formally, since we know from equation 5 that the modified duration equals this quantity here, and from the first part of equation 4 that the linear approximation for percentage change in price equals this quantity here, it follows that the linear approximation for change in price per unit shift in yield equals simply P plus minus P minus over 2. This is a better estimate of the linear approximation effect when the relationship has some element of curvature, like in this case here. We refer you to Wikipedia again, this link here, if you would like more mathematical detail on this topic. More formally, the convexity factor is P plus plus P minus minus twice the original P over 2. You might recognize this term as half the numerator from our equation 5 for the numerical approximation for convexity. You will understand why we calculate the convexity factor in this manner when we reach the final calculation of VAR. We switch now to the application of duration and convexity through their exact or analytical mathematical formulas discussed in detail in our module Bond Fundamentals. Instead of revaluing the instrument's sensitivity using shifts in risk factors, we rely here on a shortcut. We first reproduce below the main equations we intend to use. We restate first the equation for the approximate percentage change in bond price as a function of yield shift, modified duration, and convexity. The closed-end formulas for modified duration and convexity are, for modified duration, this, and for convexity, this, where N is the number of years, F is the compounding period per year, i.e. 1 in the present case, PVCFT is this quantity shown here, which is the PV of the cash flow for period T. And finally, PVTCF is the sum of the PVCFs, which is the total PV of cash flows under the bond or the security, i.e. the price. We emphasize again that these closed-form formulas are correct only for fixed-rate, option-free bonds. From these equations, it follows that the modified duration of a zero-coupon bond with maturity T, expressed in years, equals quite simply T over 1 plus ZCT, and that its convexity equals this quantity here, where ZCT, using our previous notation, is the zero coupon rate for maturity T. A shift in any particular zero coupon rate ZCT will affect the present value of the single cash flow falling at time T and none of the other cash flows. Therefore, the change in bond value for any such shift will simply equal the change in PV of that single cash flow. but we know that the percentage change in PVCFT equals this quantity here, using once again modified duration and convexity in the formula. And now applying some algebra to our previous equation leads us to the percentage change in PVCFT being this quantity here. In turn, this leads to the change in PVCFT being this quantity here. And finally, the change in the bond value specific to the zero coupon rate T equals this quantity here. We pause for a second and let you digest the algebra. We now apply these equations to our 5-year bonds cash flows in worksheet RS Bond Analytical, to which we turn next. In this worksheet RS Bond Analytical, we show the present value of each cash flow in cells F22 to F26, its modified duration in cells G22 to G26, and finally the product of these two items in cells H22 to H26. The convexity of each cash flow is then calculated in cells I22 to I26, and cells J22 to J26 in the final column here on the right calculate the product of each cash flow's PV and the cash flow convexity. The position linear sensitivities to risk factor unit shifts calculated via the closed form analytical formulas for modified duration appear here in cells C16 all the way to G16, while cells C17 to G17 right underneath calculate the convexity factor, as you can see. And this by means of the convexity formula. You should easily be able to verify that the outcomes under this approach are identical to those calculated via the numerical approximations, appearing, we remind you, in cells C16 to G17 as well, but in the preceding worksheet, RS Bond Numerical. The analytical approach via modified duration and convexity is a shortcut that avoids the trouble of the detailed revaluation for assumed shifts and opposite shifts in risk factors. Unfortunately, this approach is invalid for securities with embedded options, such as prepayment or extension options, and in such instances, the numerical approximation becomes necessary. We now return to derivative instruments, and specifically to a foreign exchange option, for which we illustrate via this worksheet RS FX option the impact on its value of its various risk factors and factor sensitivities. Assume the US bank has bought a European style 6-month Eurocall dollar put struck at the current spot of 1.4. The worksheet begins with our market data from our previous example, namely a spot of 1.40 and 6-month interest rates of 2% in US dollars and 4% in euros. The market data this time also includes one new input, namely the euro-dollar 6-month volatility, a critical element, as you know, in the pricing and risk management of any option. We therefore must contend this time with 4 risk factors, 3 being the same as in the previous example with the forward, these 3 here, and the 4th being the volatility of euro-dollar. Our first step is to price our option, which we do by means of the Garmin-Kohlhagen pricing model for FX options, discussed in detail in our module Foreign Exchange Options. The Garmin-Kohlhagen formula is programmed in cells C14 all the way to F14, with details in cells A33 to B42 here at the bottom of the worksheet. Please click on pause and make sure you are comfortable with the details of all these calculations if you wish. As before, the risk factor sensitivities are based on shifts of 1% in the FX spot rate and of an absolute 1 basis point for the 2 interest rates. For volatility, we use somewhat arbitrarily an absolute shift of 0.1%, as mentioned in Chapter 1. We need yet again to tread carefully with regard to the direction of these shifts, but you should have no difficulty confirming that the following shifts have a negative impact on the euro-call dollar put. A negative shift or decline in euro-dollar spot, a positive shift in the 6-month euro interest rate, a negative shift in the 6-month dollar interest rate, and finally a negative shift in 6-month euro-dollar volatility. Similar to the relationship between a bond's price and movements in yield, the relationship between the option price and the change in spot is not linear, but is in fact quite convex. The linear approximation and convexity factor again can be derived numerically by following the same steps that were used in the bond example, or analytically through the so-called option Greeks that will be explained shortly. In cells C17 to F17, we revalue the euro call dollar put using Garmin-Kohlhagen after applying the specified unit shifts in risk factors. Then repeat the same in cells C18 to F18, but this time using unit shifts in the opposite direction. The position's linear sensitivity using the numerical approximation is calculated in cells C19 to F19, while the convexity factor for euro-dollar spot moves is reported in cells C20 and D20. These are all calculated in the same way as in the preceding bond example. We now analytically estimate the first order effect and the convexity or second order effect through the so-called option Greeks discussed in detail in our module FX Options Greeks. The sensitivity of the option to small movements in euro-dollar spot is known as the option delta, which is calculated in cell D25. Convexity is measured through another Greek known as gamma, calculated in cell D26. Recall that delta and gamma are to options what modified duration and convexity are to bonds. Formally, we say that these are first and second derivatives of the price with respect to a change in the relevant underlying, which would be the yield in the case of bonds and is the spot here in the case of options. Vega is the Greek that reflects the impact on the option price of changes in volatility, and its value is programmed in cell D27. Finally, row 1 and row 2 reflect the impact of movements in the US dollar and euro interest rates, respectively, and are programmed in these two cells, D28 and D29. In these cells here, from C21 and over to the right, D21 to G21, we translate the delta, vega, row 1 and row 2 figures into actual position sensitivities to shifts in these risk factors. While in this cell here, D22, we calculate the convexity factor using the formula for gamma. Please click pause and take your time if you need it to make sure you are comfortable with all these calculations. Again, the results we obtain from both numerical and analytical methods are almost exactly equal. A shortcut is again available via an analytical approximation shown below based on the Greeks. Here it is in reasonably comprehensible layperson's term, and here it is in slightly more technical mathematician's terms. Specifically, the change in the value of the option is a function of delta multiplied by the change in the spot plus half gamma multiplied by the square of the change in the spot plus vega times the change in vol plus the first row times the change in the term currency interest rate, and finally plus the second row times the change in the base currency interest rate. However, besides plain vanilla options and a small minority of exotic options, closed form formulas for Greeks are not usually available, and numerical approximation becomes the only alternative. So we will not spend any further time discussing the analytical approximation. Our final illustration of a VaR calculation for a derivative instrument centers around an interest rate swap. Suppose the U.S. bank has just entered into a U.S. dollar interest rate swap with the following characteristics, where the bank is paying fixed and receiving floating. By analogy with the fixed rate bond we discussed earlier, you should readily understand that the valuation of the swap requires various inputs from the zero coupon yield curve, and specifically the 1, 2, 3, 4, and 5-year zero coupon rates, which therefore represent the complete set of risk factors for this position. As with bonds, the relationship between swap values and movements in interest rates is subject to a degree of convexity. We will therefore use the numerical method in an analogous way to that from the bond example to estimate both the position's linear sensitivities to risk factor shifts as well as the convexity effects. In this worksheet, our SIR swap, cells C25 to C29 contain the zero coupon spot rates for the relevant tenors. In this table here, labeled base case scenario, we value this interest rate swap in the same manner as we explained in our module Interest Rate Forwards and Swaps, starting with the calculation of the LIBOR curve in cells E25 to E29. The PVs of the fixed payments made by the bank under the swap appear then in cells F25 to F29, while the PVs of the floating payments received by the bank based on the spot and forward LIBOR curve appear in cells G25 to G29. The fair value of the swap, which is simply the difference between the aggregate fixed PV and the aggregate floating PV, is calculated in cell G31 and is equal to negative $20,919. Again, our module Interest Rate Forwards and Swaps provides extensive details on all these calculations. In the tables beginning in row 33, we revalue the swap position after giving effect to unit shifts in both directions in the individual risk factors, exactly as we did earlier for the bond. The swap fair values resulting from upward unit shifts in risk factors are summarized in cells C18 to G18, and the ones from downward shifts in cells C19 to G19. The position linear sensitivities to these unit shifts in the risk factors are calculated in cells C20 to G20, being in each case half the difference between the position values after the upward shifts minus the position values after the downward shifts. In cells C21 to G21, we calculate the convexity factor, which is again equal to half the sum of the position values following application of the upward and downward shifts minus twice the position's initial value, exactly in conformity with the formula we had shown. Pausing for a moment to ponder the linear sensitivities in cells C20 to G20, we see that except for cell C20, the position sensitivity increases with tenor in a manner very similar to what we observed in the bond example discussed a little earlier. Indeed, the pay-fixed swap is equivalent from a risk perspective to a combination of two bond positions, long an FRN paying 12-month LIBOR, and short a 5-year fixed-rate bond whose coupon equals the swap rate. The linear sensitivity and convexity measures are also seen to equal those for a short fixed-rate 5-year bond minus those for a long 5-year FRN. You can verify this by returning to worksheets RS bond numeric and RS FRN and confirming that the bond price sensitivity to opposite shifts in the risk factors minus the FRN price sensitivity to these shifts equals almost exactly the swap sensitivity to these shifts. The very minor difference that you will find stems from the fact that the IRS rate here is 4.95%, while the coupon of the bond in those earlier worksheets was 5%. This concludes our discussion of risk factors and the measurement of risk sensitivities, and brings us to the end of this chapter 2 and of part 1 of this module.